So what are absolute or third law entropies? Well, entropy is fundamentally different from energy in that we have this way to fix its value and not just look at changes in entropy, but actual absolute values for entropy. And that goes back to Boltzmann's equation, statistical equation for entropy. And we know that this implies, since the number of microstates at absolute zero is going to be equal to 1, log of that 0, so we get that if we're at absolute 0, then as long as we have a perfect crystal, the entropy is going to be equal to 0, which means that we have a fixed reference point. And so if we were to graph the heat capacity as a function of the temperature, we'd see that it goes up as we get higher in temperature. And we know that if we integrate Cp dt over T, we're going to get delta S. In other words, how much if we integrate from T1 to T2, we can get how much entropy increases. And so since we know that we're starting at absolute 0 with 0 entropy, any entropy we add is just added to 0, and we can get an absolute number for the entropy change, the entropy of a substance. And so this integral does not work out when we go to absolute 0, and so there's a way to model this last little bit of the curve that's called the Debye Extrapolation, and you can read about that in your textbook. But for now, imagine that we have a couple of temperatures here. I'll call that T1. We've got the melting temperature. Then later on, we've got the boiling temperature. Let's imagine we're talking about something like oxygen, which is a gas. Well, how would we find out its absolute entropy at room temperature? What you do is you'd say its entropy at 298 is equal to the entropy at absolute 0, which would be 0, plus, well, we'd have to integrate Cp of the solid, oops, let's put a little s in here for solid, from 0 to T1. We'd have to, and like I said, just look in your book for Debye extrapolation. I'm not really focused on that, but anyway, that's how we can model that first part. And then as we heat up any solid, we look at the heat capacity of the solid, and we integrate that from the melting temperature until we get to the melting temperature. Well then, let's go ahead and wrap this around a little bit. We melt. Well, we know that we get a change in entropy just from melting, so we have to add that in. Remember that the heat of melting is actually called the heat of fusion. And then we'd have to heat up the liquid, so we have to integrate from the melting temperature, and since we have oxygen, we know we're eventually going to boil because we're going to form the gas phase, and so we have to be careful and switch this to the heat capacity of the liquid, since we're integrating liquid from melting temperature to boiling. And then we get another entropy change due to boiling, so we have the heat of vaporization over the boiling temperature. And finally, we'd integrate from the boiling temperature of oxygen to 298 kelvins. And that would be, since we're dealing with a gas at that point, we look at the gas heat capacity. Okay, so in theory, we can measure all these heat capacities, and there's actually ways to calculate them from theory as well. So we can have measured heat capacities, theoretical heat capacities, and they actually agree pretty well. And we can integrate those. We do all these integrals, we end up with a number. And that number is the actual amount of entropy that is in oxygen gas at that temperature, 298. So in the back of Atkins, there's a table of absolute entropies for a bunch of different compounds. And notice that it's not delta S, it's the actual entropy of that compound at a specific temperature. And so we can use these in calculations. So anyway, those are absolute entropies.